Hello everyone. Today is day 25 of the challenge, and the problem for today is to implement a cycle GAN for style transfer, where we have to convert horse to zebra crossing. Uh, then we'll have to train on a smaller image set. Uh, okay, let's see. Let's go and use the same ChatGPT context window. Say, hey, it is day 25 and the problem state is okay, let's wait for what it is going to generate today. Let me go come to the bottom. Just a second, guys. I have a cat who is searching for something, so I'll need to go. Let's see what it says, what we have to do. Just a second. Okay, sorry. So yes, if we look at the code is that what we'll see what cycle GAN is. So it is a powerful approach for style transfer where we convert one type of image to another type of image and vice versa without needing pair images. We'll all give you the full implementation. Okay, so this is an approach where we can transfer where we convert one type of image to another type of image, for example, horse to zebra. Without needing paired images below, I'll give you full implementation to set up and train a cycle GAN for a simple use case. Before diving into the implementation, here's what we'll do. First, we will understand the cycle GAN. The cycle GAN consists of two generators and two discriminator. Okay, this is something new. So it consists of two generators and two discriminator. Generator G converts images from domain A to domain B, that is horse to zebra. Generator F converts images from domain B to domain A. Again, oh, nice, from zebra back to horse. And discriminator DA and DB ensures that generated images from other domain look realistic. Okay, so ensures discriminators DA and DB, they ensure that the generated images from the other domain look realistic. Okay, so they will make sure that the images generated, they look realistic. We also can use cycles consistency loss, which is like this. We will also use okay, cool. The data set is that we'll use images for style transfer such as horse to zebra, money to photo from the publicly available data sets. Okay, and below is the full code for it. What data set are we using? We are using the data set. What is TFDF? You're using this TensorFlow dataset as DFDF. Okay, we process the image, build the generator, build discriminator, and combine for GAN model and build the combined model. I'm just curious, is there any better way for doing? I am curious to know if there is any better way to re- other way to read the epochs to train on epochs. It is a lengthy a core just for iterating over epochs? I'm just curious because we are doing some sort of similar things. Is there any better way of doing that? Hmm. This is even more lengthier. Let's rely on this one only. Okay. So let's start coding. Hmm. Minimize this terminal. Close it. Create a new file. Call it day25.py. Add it to the Git repository. And the problem is going to be this one. Let's import the files. Let's import the libraries. SDF. How many layers you want? Input conversion, 2D conversion, 2D transport, leaky, rectifier linear unit, rectifier linear unit, patch normalization, and concatenate. These are all the layers that we had used yesterday. So let's import them. I'm copying it because it takes a lot of time to. Then import TensorFlow dot keras dot models. Import models. Import NumPy as a NumPy. Import matplot.py.sblt. Import OS. Import glow from TensorFlow. Okay, we'll pass a learning rate here. So that is why we are importing the optimizer. So let's load the data set. Load the data set. Horse to zebra from the uh, I'm going to say actually the problem is split into, I guess it is split into two things. Today we just have to implement the recycle. So we'll implement the training problem split into 2 days. Today we have to implement it, and tomorrow uh, we will train it. Can you give code according to that? Also, keep the code in uh, as normal training loop. Hmm. Okay, yes, that's what I was doing. We have to build the discriminator and combine the discriminator and the and what uh, generator. And on day 26, we will be training the loop. So let's start. Let's metadata import TensorFlow dataset data data sets as tf df dataset tfds. So we'll use tfds dot load cycle. So I'll just copy it. CycleGAN or to Zebra. Can I see if this is linkable? Okay, this is not linkable. Okay, and then we'll do what? Just give me a second, right? So this is it. Let's come here, and here we pass with info yes as supervised room. So we pass with info. Correct. So we have the data set. Now we are going to load the train A, train B. So it will be train horses and train zebras. And it will be data set train A, data set train B. So let's look at the data set. Print train horses, print train zebras. So let's do what? Let's run this file. Let's run this file. Python d25.py, and we have an error. So it says this has no attribute called. Okay, so it says this is what we have to input. I'll say pip install. So I'm installing the TensorFlow datasets. So I'll say import TensorFlow datasets as tfds, and let's run the file. Clear the terminal. Run the file. Okay, so it does not exist. I'm getting this error. So this does not exist though. We are not even able to download the dataset. says we can download it directly from horse to um, zebra dataset. So if I go to this dataset and see the dataset here, so it is test A. Sorry, so we'll go to train A, train B. Train A, train B. Okay, so train A images they look like this. Horses images look like this. And the zebra images they look like this. Just a second here. क्या हुआ बच्चा? क्या हुआ? Yes, so the zebra images they look like this. So we let's go and download them. So I'm going to download the dataset here like this. Let me see where can I download it. Hmm. Let me pause it and download the dataset first, and then we can figure it out. Continue it. Okay, so I've downloaded the dataset and I have also moved it to a folder inside my dataset called horse to zebra. And here we can see all the images under train A and train B. So now we are going to load that directly. So what are we going to do? Go back to the code here, and then we mention the path of the directories for horse and zebra. So we'll say horse directory is going to be dataset horse to zebra train A, and zebra directory dataset horse to zebra train B. So we have got the directory. Then we'll do what? Helper function to load images from the directory. So we'll have helper function to load images from directories. So we know how the images they look like. So let's load it from the directory. So we mention the size. Then we open from the globe the images, load the image, convert it to array, and then append the array vector array into this vector into this images list, and then return it into a numpy array. So we'll def load images from directory. Here we mention what? Directory, and then the size. The default size is 128 into 128 pixel. Let's create a images list, then iterate to file path in globe os dot path dot join this direct JPG. Then I've got images. Load image. I'll have to import this function. So I'll be importing the function. I'll remove this from TensorFlow keras dot preprocessing dot image load image. Okay, so we have load image. Here we pass the file path, and the target size is the size, and then this is the image. And then we convert image to array, image to array, image to array. Pass this image, and then we simply append this images append this image and return the numpy array form of this images list. That's it. Now we are going to load all the images. Load heroes and not heroes, horses and zebra images. So it is image horse images. We'll pass it to this horse directly, and then we'll pass zebra images load mention the zebra directory. We have the images. Now if you remember, let's all these images, if we see, all these images are in the, let's click on it in the black and white format, sorry, color format. So what are we going to do? Let's read it. Now we are converting them into grayscale images. So we are normalizing. Load images are normalized with the range -1 1. Why? Because 10h function usually works with this within this range. The TensorFlow dataset API is then used to create a dataset from the NumPy arrays and batch them. Okay, then we will use the TensorFlow's dataset libraries, this function from TensorFlow slices to convert these arrays, NumPy arrays, to the uh, uh, TensorFlow arrays and batch them. With this approach, the dataset is loaded locally, which means you won't have to rely on the original TensorFlow dataset. Okay. So let's do what, normalize it. I'm just going to say we are doing it because of 10h activation function or anything else. Yes, correct. Additional, can you please be brief? See, 10h activation is the main reason, but it also helps in stabilizing the GAN training, by making sure discriminator and the generator learn effectively. Correct. So let's do what? Let's come back to the code here. So horse images, let's normalize them. So horse images, and we all know why we are doing it. We have done that like on two of our previous problems. We know why we are doing it, because this is the half of the 256 to so 127.5. So if you want to know why we are doing it, I would recommend do a bit of calculation on some random numbers like 0, 255, 138, so you'll understand. Now I'm going to do the same on the zebra images, and then we will convert to TensorFlow datasets and batch them. Convert to TensorFlow dataset and batch them. So train horses. So we'll do what? Import this from TensorFlow keras dot for data dot date dataset from. I'll say let's import this dataset from tensor slice and mention the horse images and batch them, and then do the same for the zebras and zebra images. So we are done with the step number one, loading the images perfectly. Now we'll do what? Build the generator model. So we'll build a generator model. So the generator model is going to be, I guess, same here, except the shape is 128 by 28 and three channels. We'll start with 64 uh, neurons, and everything is going to be same that we have already explored like twice and thrice in our previous problem. So we'll just see and copy and paste this time, because it takes a lot of time to type. And then we go from 64 to 128 to 256, and then we unsample them and then return the model. So let's do what? Let's copy it, and then we are going to build the model. So build the generators for both transformer and both transformations. So we'll say build generator for both transformations, A to B, B to A. So we are going to be generator G is going to be build generator, and generator F is going to be build generator. First one is horse to zebra, second is zebra to horse. Let's capitalize it, and then let's see the summary zebra f dot summary. That's it. Let's now build the discriminator model. Build the discriminator. So if we say here also we are starting with the same dimensions, and then we have patch normalization, leaky rectified linear unit. We are starting with 64. If we see here also we are starting with 64. We'll go 128 and 256. The same way we are doing with discrimination, and then we have one convolution layer, output convolution layer of kernel size 4. So we build that. So I'm going to copy this as well, code to this, because why I'm copying this is because we have already explored this section like twice and thrice and typing every time the same thing. So we can optimize that by learning something new today. So now we will build the discriminator for both domains. So we'll say discriminator G A domain A build discriminator. So for domain A, which is horses, and discriminator B build discriminator for domain B, which is zebra. That's it. Horses capital H, zebra capital. Done. Now we'll do what? Compile with the model. So dot A dot compile. Here we pass the Adam, sorry, optimizer as Adam with learning rate 0.002, correct? And beta, and here beta 0.5. Here the matrix is loss function is, sorry, first we'll say loss is mean square error, matrix is accuracy, and the same we will have compile the domain to discriminator. Let's have good number of spaces so that the code remains in the center, and then we'll print the summary of discriminator A and discriminator B. So discriminator A dot summary. Let's move in the same order as we are defining. Now we are building the combined cycle GAN model. So generator G converts domain A to B. Generator F converts domain B to A. Cycle. So that is A to B, B to A is a cycle, no? So that is why it is called GAN model. Cycle consistency loss ensures that if we translate an image to the other domain and back, we get the original. So the cycle consistency loss is that when we generate an image from A to B and then generate again from B to A, then we are going to receive the same original image. So that is what the cycle consistency loss ensures, and this is what the cycle GAN model is. So let's do that. Build cycle GAN model. So what I'm doing, define the combined cycle model. So we are defining the combined cycle GAN model, and we have a typo. So what I'm doing, def build combine. Here we take what? Generator G, generator F, discriminator A, discriminator F. So we are A, B. So we'll say generator A, generator B, and we don't have that. So we call G, F, discriminator A, discriminator B. And then we again same thing, we turn the trainable configuration for both of our discriminators off. So discriminator A dot, let's do what, let's write the code later. let's build the discriminator and print the summary. So we'll say come model and use the combine pass the generator a g, generator f, discriminator a, discriminator b, and then let's do what, print the summary. This is what we have to do. That's it. So let's build the model. Before that, let's do what, discriminator a dot trainable of, discriminator b trainable of, and then we'll do what, real input images. So we are going to uh, pass in the real input images for both domains. Real input images for both the domain. We'll say input a is going to be input. Shape it will be same as we had here. So 128, 123 for domain, for this is for horses, and then we'll have input the shape 128, 128, 3 zebra. Then we'll do what, cycle. Achha, okay, so first we have forward cycle and then we have backward cycle. So forward cycle is a to b to a. So first we generate from a horses to b, and then again from b to a. We do the same with r, and then we'll do backward cycle b a b. Okay, first forward cycle a to b to a. So we'll say we'll have like uh, the generator will generate the fake images, right? So generator g, here we pass the input a which generates the input b, and then we get the cycle a, cycle generating b from a generating b, and then we generate, use the f domain to, here we pass the fake b which generates the cycle a, right? And then we do backward cycle which is b to a to b, and here we are first generating fake a by using the first generator with will pass the input b, pass input b, generate fake a, then generate back the b by using generator domain to domain b generator and pass the fake a. So that's it. We have generated both the completed both the cycle. Now identify mapping for preserving original features. Okay. Okay, so we are getting the so identifying mapping for preserving original features. So let's get the from the original ones. Same a identify we'll have generator G F. Here we pass the input A. Generator. Okay, we are using FG. First G domain A to B. So here we are using B to A F G. Correct. From A to B always G. B to A F. From B to A F, फिर A to B G. Correct. I was using wrong. So will A to A is F, and where B is the start we use F. B is the start. Okay. Same B. Generator G. Input B. We got the same original feature image. If we get the original, so whatever input images that we have created, we are now getting this from the original. Okay, so from the original, we are getting the original features from the generator. Now discriminators for generated images. Discriminators for the generated images will do what? Valid A. So discriminator A, we pass the fake A, and check the validity for B, pass it to the discriminator for domain B, pass the B images, fake B. Then we are going to do what? Define the combined model. Define the combined model. So we'll do what? Model is equals to model. Here we pass the input shape is, so the inputs are input A. For a model input are input A and B, and then we have output are what are the inputs? Valid A, valid B, cycle A, cycle B, same A, same B. Okay, valid A, valid B, cycle A, cycle B, and then same A, same B. Okay, and then we are going to compile the model.compile. Learning optimizer is with learning. Okay, same. Adam with learning rate 0.0002. Beta 1 is 0.2. Sorry, 0.5. Loss we'll get from so loss for outputs we'll have 1 2 3 4 5 6, 1 2 3 4 5 6, and then the loss weights are 1 1 10 10 5 5. I'll ask why we doing this. Why are we doing this? So this line compiles the cycle combined model. Each part of it has a specific role in ensuring effective training. So if we break it down, the mean squared error used for discriminator losses to differentiate between real and the fake images. That is why we have it for 6 of our outputs. The for the two cycle consistency, and for the two for identifying mapping, ensuring that the original features are preserved when converting back to the original domains. That is why we have it for 6 times. Basically, to get the use for the discriminator losses to differentiate between the real and the fake images. Then we have loss weights. Represent the importance assigned to each loss during training. 1 1 are the discriminated losses. are weighed normally. 1010 cycle consistency losses are crucial to ensure transformation does not lose information, so they are weighed heavily. Okay, here we see these are very important. These are the cycle uh, outputs, so we want to keep them, that is, as in we want to give them higher priority, that is why more weight. And then identify loss, uh, uh, to this will help the model maintain the original images features, so they are given significant slight less but more than the cycle discriminator loss. So this is for the discriminator loss that we have generated. These are the cyclic images that we have generated here, A and B. So this is for the for those, and then this is for the original images. That is why it is a little higher but lesser than the cycle one. This is what you want to make sure that it is the original image, right? Has the minimum loss. So that is why we are doing it. So we'll say loss is going to be mean square error, and then let's keep it how many times? 6 times. Not this. 1 2 3 4 5 6, and then we have matrix, and the matrix is going to be 1 1. Matrix, not matrix, loss weight. Loss weights are going to be 1 1. This will have the highest weight importance, so it will be 10 10. And then we want to keep the original features also preserved, so we'll have give a slightly more uh, weight. And let's go back to the code, not this one. Yes, this is it. So then we will simply return the model, and this is the model. This is the model. Let me run it once. We are not training the model. Just see, we are not training anywhere. We will do that tomorrow. But let's run it so that we can see if we have any error. We have error at line number 22, which is 22. What is the line number 22? So it says this is not running nicely on my system, so I need to see, maybe we'll have to import it. So it is a model, not a function. uh, if And it basically used as if it were a callable. Instead we need to, for file path in glob os.path.join with from globe import globe. Okay, from globe import globe. Now it should run fine. Okay, so it is running fine. This is how our discriminator looks. This is how our generator is looking. So yes, it is looking fine. Let's go and commit the code. Come back tomorrow and train it and see if our model will be correctly able to generate the original image after changing it to domain, from domain A to B and then back to B. So what is the loss there? So we'll add the D25, commit, add, and D25 train cycle can. sorry, let's amend it. Not train will do tomorrow. Implement, and then push it. See, we are able to see the data set. Yes, day 25. Let's mention one more thing, the data set. This is the data set information. So yes, let's wrap it up for today and come back tomorrow and train the model. And thank you very much.